let's go back to our discussion of the solar system as a whole. When I was in elementary school, even college for me, this is what our view of the solar system was. The inner planets, Mercury, Venus, Earth, and Mars, followed by the larger planets, Jupiter, Saturn, Uranus, and Neptune, with then this one oddity, Pluto, a planet smaller than the inner planets, yet way out in the outer portion of our solar system. And Pluto's orbit always seemed kind of strange. It was moving on an orbit that was highly eccentric, actually crossing Neptune's orbit as it plunges a little bit closer to the sun. We now have a much broader view of the solar system. We now, through astronomical observations, have enriched our understanding, and our view of the solar system now looks more like this. We've got the inner solar system, Jupiter, Saturn, Uranus, and Neptune. We now recognize that Pluto is but one of 50 or perhaps more dwarf planets that make up part of the Kuiper belt. This represents, as we'll discuss later, the leftover pieces of planet formation. And Pluto doesn't seem very special. When we compare Pluto to some of the other dwarf planets, this is some of the dwarf planets that have been discovered. This is their distance from the sun, measured in astronomical units. Remember, it's 1 astronomical unit from the Earth to the sun. So Pluto is typically about 40 times the distance of the Earth from the sun. And you can see there's several other dwarf planets at comparable distances. Sedna right now stands out as the most distant of the set we're looking at. This column here shows the sizes of these planets. And you can see that Eris is actually a little bit bigger, and there really are a host of dwarf planets of comparable size and comparable properties to Pluto. This is why astronomers were stuck with the choice of either classifying Pluto as not being a planet or requiring elementary school children everywhere to start memorizing the list of 58 or so dwarf planets that were part of our list of planets that we'd like to know about. And we were kind and demoted Pluto and put it in a special category where I think it really belongs, given its properties. It really does look much more like these dwarfs, both in terms of its orbit and its size. Now, let's talk a little bit about how these are discovered. Here's one of the recently discovered dwarf planets. And here it is with its moon. These planets are discovered through an effect called parallax. The way parallax works, and you can do this experiment right now, hold out your finger in front of your face, close first your left eye, then your right eye. Repeat that. As you do that, you should find that your finger moves relative to the background behind it. The same thing happens as the Earth orbits around the sun and we view these dwarf planets. As the Earth moves around the sun, our orientation relative to that planet changes. So its position relative to the background stars shift. And here is how Sedna was discovered. Here is Sedna, and here are some background stars. And if you measure the position carefully, you could see that Sedna has shifted relative to those background stars. And that shift in position, just over a few hours, was enough for astronomers to realize that Sedna was much closer. The amplitude of this parallax effect depends upon the distance to the planet or star. If you take your finger, hold it close to your face, blink back and forth, it moves a great deal. Further away, it moves less. And it's this effect that we use to measure the distances to stars. One of the things astronomers have recognized for a long time now is our sun is but one of many stars in our galaxy. And the difference is the other stars are much further away. When we look at the night sky, the nearest star to us is the Alpha Centauri Proxima Centauri set. They're the nearest star after the Sun. Those of you who live in the southern hemisphere have certainly seen Alpha Centauri. For those of you in the northern hemisphere, the star that's easiest to see in the night sky is Sirius. That's the dog star. It's the very bright star you see. That's not a planet. Remember what we discussed before. Stars twinkle, so Sirius is the brightest object twinkling. Planets, like Jupiter and Venus, because they're closer and bigger, don't twinkle. So let me encourage you to go out tonight, depending whether you're in the northern or southern hemisphere, and try to identify some of the brightest stars. Astronomers use this same parallax effect to measure the distance to the nearest stars. They observe what the star's position is as a function of the year, where the star is in March, where it is in September. If the star is close, its positions will shift relative to the background stars. We measure that shift in angle in what we call arc seconds. Now let me just remind you about the properties of angles. We divide a circle into 360 degrees, and we divide each degree into 60 arc minutes, each arc minute into 60 arc seconds. So 1 degree is 3,600 arc seconds. The parallax that a typical nearby star would have is about an arc second. So a star whose parallax, how much the angle it moves relative to the background star, if it has a parallax of 1 arc second, its distance is a parsec. And that's the unit we use to discuss distances to stars. 1 parsec is about 3.26 light years. Recall a light year is the distance that light travels in a year. We could also compare it to an astronomical unit. The astronomical unit is the distance between the Earth and the Sun. The nearest star is about 200,000 times further away than the Sun. Space is pretty empty. There's a lot of space between stars. Our solar system, at least the part we can see with the planets, occupies a very small volume of the distance between the stars. Even if we go out towards Neptune, Neptune's 40 astronomical units. The nearest star is 200,000 astronomical units. To convert that into even more familiar units, that's 30.9 trillion kilometers, or representing it in meters, 3 times 10 to the 16 meters. Let me remind you of how scientific notation works. This means 3 followed by 16 zeros. So measured in meters, the nearest star is pretty far away. And that nearest star is but one of many stars in our galaxy, the Milky Way. Here's an image of our galaxy, the Milky Way, taken by the COBE satellite. And what you're seeing here is literally billions of stars. Most of the young stars in our galaxy arrange themselves in a disk, and you can see this disk here. Our Sun is one of the stars in our disk galaxy. The center of our galaxy forms what we call a bulge. It's a somewhat bar-shaped bulge. And the stars you see here in this picture are nearby stars. Our disk has a finite thickness, and when we look through it, these are some of the stars closest to us that we see up here. The distance to a typical star up here might be 10 or 100 parsecs, or equivalently about 30 or 300 light years. The distance to the center of our galaxy is about 8,000 parsecs, or 24,000 light years. That means it would take light 24,000 years to get from the center of our galaxy to us. And our galaxy is but one, as we'll see, of many galaxies. Here's a top view of our galaxy. We are about here. It's about 8,000 parsecs from us to the center. all the way across the disk is about 30,000 parsecs, or equivalently about 90,000 light years. When you look at our galaxy in detail, you see that it has a bar, a ring of young stars around that bar, and then these spiral arms. The spiral arms are the region of active star formation in our galaxy. So most of the young stars are forming here in the spiral arms, and then they spread throughout the disk of our galaxy. So now let's turn to the next set of questions. Let's calculate how long it takes to reach from us to the nearest star. And then if we travel at 10 kilometers a second, or 1/30,000th the speed of light, how long would it take our rockets, today's conventional rockets, to get to the nearest star? And finally, how long does it take light to get to the center of our galaxy? Let me remind you, what you're going to do is exit this video, answer these questions, and then come back to the video. For these quantitative questions, you don't need to give an exactly correct answer. We'll accept any answer within 20% of this value. The idea in these problems are to give you somewhat of a quantitative feel of how big our galaxy really is.